All right, in this video, we're going to prove the doubling time video. Actually, we're going to derive the doubling time formula. So I have the results listed up top. Those are simple to manipulate to get each one, right? If I start with this original one, if I divide by k, I would have one of them. And if I divide by t, I would have the other. Another quick thing to mention is this is for exponential growth models, right? Not every function will have this doubling time. So in exponential growth, remember that there are different ways to write the model, but one way is P of t equals P sub 0 or P naught e to the kt. Now, what does all that mean? The P naught is the initial value, right? So P naught is the initial value. It could be population or it could be uh, dollars or I mean whatever the word problem, right? Whatever problem you're looking at, it's the initial, it's a start. K is the growth rate. So in a percent, right, we would just change it to a decimal. So if something is growing at, say, we'll do an example at the end. So like it's growing at 5.4%, let's say. Okay, that would be our K. T is the time in years. Okay, how long is this thing going? And that's kind of the question here. And P of t is our final value, right? Like after t years, what value are we at? So the value after t years. Okay, so we're going to look at doubling time. So if I started with some value, doesn't matter what that value is, right? I could stick with P naught. If P naught is the initial, then my ending value is double that. So that's how I'm going to approach this. I'm going to start with a generic P naught, and I know I should end with double that because we're deriving this doubling time. Okay, how long does it take to double? And then e to the kt, we don't know the growth rate or the time. The doubling time will depend on that. And the difference in what I wrote above, which many textbooks do, they use a capital T to denote like that is the doubling time. Okay. All right, well, let's solve this. First things first, I don't like that P naught, and it's on both sides. We have all multiplication, right? So let's divide it. I didn't mean to do Christmas colors here, but that's all right. So if I divide P naught on both sides, I simply get 2 equals e to the kt. And we know how to get the variables out of the exponent, right? We do natural log. So the next line, I'll go ahead and write another line just so we can space it out. But really, I would have just wrote ln on both sides because that cancels the e and essentially, right, brings the kt down by the power rule of logarithms. So now we have kt equals ln2. And that's it, right? That was the first form of the formula. If we knew the doubling time, which we now denote as a capital T, we could find the growth rate, right? So I could divide both sides by this T. So again, we're just going to change this T to a capital to say like this is the doubling time. It is a specific time, right? So then we can divide by t and get k equals ln2 over t. Or we could have started, right, and go back to the initial and divided both sides by k to get t equals ln2 over k. So if you know the growth rate, take ln2 divided by that growth rate. If you know the doubling time, take ln2 divided by the doubling time. So as I said, we would do one example here. So suppose I knew the growth rate is 5.4%, like you made some investment, right? I don't care how much it is, $10 or $100,000. But if I knew I was getting a 5.4% return, now this is continuous compounding in my example, right? It's an exponential growth model. It has to be an exponential growth model for this formula to work. But all you do to get this doubling time, you just take ln2 and you divide by 0.054, since 5.4% as a decimal, you move it twice, right? It's 0.054. And plug that in your calculator, because I cannot do ln2 divided by 0.054 in my head, not even if I tried. And you get about 12.8. Remember, we're in t time, which is years. So something growing at a 5.4% rate would double in, close to 13 years.